Okay, so hello everyone. Um, this video it will be about solving conic sections in a way that many people don't. That is using linear algebra, and many people do solve it in this way. So I learned this from a video from Dr. Payam. You should watch that. And I could only learn that because I had watched the 3 Blue 1 Brown series of like Essence of Linear Algebra. So because of that, I could actually understand what's going on and the details of that. Which, let's be honest, he skipped some details, I think. And the last example of the hyperbola, he sketched that incorrectly. Whatever. Let's not nag about that because right now I have written all of this down. So I want to explain all of this. Alright, let's start from the very basics first of all. So how do you diagonalize a matrix and what exactly does diagonalization do? So first of all, some notation. Usually I use this box notation for the scalar triple product, that is the determinant of the matrix. But here I will just use this for the matrix itself. So what you have to do is that think of these vectors as column vectors and then stack them up, and the matrix that you will get is represented by this box notation, right? So this is the matrix made out of column vectors, v1 vector, v2 vector, v3 vector. Okay, and now the real thing starts about diagonalization. So the idea goes like this: if you have a matrix that has eigenvectors v1 vector, v2 vector, and v3 vectors, which are basically like vectors that have this property that when you apply the matrix on it, it just returns lambda 1. We'll just say that's the constant, right? So matrix applied on v1 vector, that will just return lambda 1 times v1 vector. That is, they just scale down or up by a factor. They don't change their orientation, right? So you have vectors like that for some matrices. So these are called eigenvectors, and then the factor by which they scale up or down, that's called the eigenvalue. So if you have a matrix M and the matrix M has eigenvectors which are now in 3D space, so there are 3 such vectors for this matrix M with eigenvalues, the corresponding eigenvalues lambda 1, lambda 2, lambda 3. And of course this also means that anything along this vector will also do the same thing. So when we say eigenvectors, our eigenvectors are not unique, right? Their directions are unique, yes, but they themselves are not unique. You can just multiply by them a scalar and then they are still having this property, right? So that's why I say they're not unique and not using any formal definition, right? That's why I can say they are not unique. Anyway, but you know, saying any vector like this is an eigenvector, that also yeah, like that also clarifies why you know, this R matrix that we're going to get later on is not a unique matrix, and why you could have multiple different ways of diagonalizing your matrix M. Anyway, first of all, what I'm saying is, if your matrix M has, so yeah, this operation has 3 eigenvectors because we are in 3D space with the corresponding eigenvalues lambda 1, lambda 2, lambda 3, then you can write any vector in that 3D space as a v1 vector plus b v2 vector plus c v3 vector, assuming that v1 vector, v2 vector, and v3 vector are independent, right? So you can write any vector in our 3D space as this thing, right? Basically just, you know, resolve our vectors. So yeah, this is, I mean, really doable. Just, you know, use the reciprocal matrix or something like that. I don't know, use whatever you want to do and get this thing done, right? And then once you have this, just apply the matrix on it, right? So apply the matrix on this general vector v vector, and then you'll just distribute our matrix because, you know, it's a linear operation. So distribute our matrix and you will get this thing: a m v1 vector plus b m v2 vector plus c m v3 vector. And then using the definition of the eigenvectors, you can write this as a lambda 1 v1 vector plus, yeah, you get the thing. And then you can write it like this: so v1 vector, v2 vector, v2 vector, v3 vector, right? These column vectors, the matrix made out of these things, that applied on a lambda 1, b lambda 2, and c lambda 3. And then you can write this vector like this: so it's lambda 1, lambda 2, lambda 3 on the diagonal, and then you have abc. So notice that as you vary abc, your v vector changes, right? So abc, when you let them be any kind of real number, you get the whole 3D space basically. right? And also once you know what v vector is, you can actually get abc. So that's what we'll do. We'll try to figure out what abc actually are. So first of all, we can write v vector as this matrix v1 v2 v3, and then that applied on the column vector abc. So then just applying the inverse matrix on both sides, you just get and actually let's call this thing as x vector. So this is our r and this thing is our x vector, and you're just applying r inverse on both sides. So you'll just have x vector equal to r inverse of e vector, and then input that thing in here. So you'll just get m v vector is equal to r d x vector equal to r d r inverse v vector. But then this happens for all kinds of v vectors, right? So yeah, what you could do is just remove these v vectors and then say that these operations are basically the same, right? So m, this matrix, is in fact equal to r d r inverse. So notice what we just did is that you basically did a change of basis kind of thing. So what you will do is whenever you will apply this matrix on some other matrix, first you have to apply r inverse, right? So that's like saying you are converting your xyz to abc, right? So in the abc state, this is getting weird, but whatever. So you convert to abcs, then you do operations on abcs, and then you once again you convert back to xyz, right? And yeah, that's what this is doing. Okay, so the matrix R is not unique, as I just told you. You can just scale up the eigenvectors, so one of these eigenvectors. So instead of v1 vector, you just have two v1 vector, right? And call that thing as v1 vector instead. And so you just get a new R a new R matrix, but then your like your representation is still going to work. So that's why matrix R is not unique. But your D matrix, so the diagonalized, right, this matrix, this is in fact unique. Yeah, because your lambda 1, lambda 2, lambda 3, right, these are unique. At least their ratio is. So you can definitely take out a constant from this thing. Okay, all that is doable, but at least the ratio is the same everywhere, right? Because the matrix M is a fixed thing. Okay. So this representation, so doing this thing, writing M as RDR inverse, this is called diagonalization. Okay, and the same process works for any n into n matrix, but we are specifically interested in 2 into 2 symmetric matrices. So here's the new thing, it's supposed to be symmetric. So yeah, that is important, because only when your matrix is symmetric that is when you can have some nice properties, and we'll see what those nice properties are. Anyway, so some new notation, which is actually not new. Many of you, I think, already use this notation. So it's basically this thing, c sub theta, basically c subscript theta, that is equal to cosine of theta, and similarly s sub theta, that is sine of theta. Okay, so since we can take out some constant from our v1 vector, v2 vector, right, we can do that kind of thing. Why don't we just convert that to a unit vector, right? That will be the best thing you can do. So let's just say v1 vector is like this, cosine alpha comma sine alpha, and v2 vector is cosine beta comma sine beta. Then write your R matrix, find the inverse of this thing, write your M matrix, calculate the whole thing, right? And then think about it, when is this matrix going to be a symmetric matrix? Well, that happens when this equation is satisfied, but that can be satisfied for these two conditions. One of the conditions basically means that your eigen vectors were in fact orthogonal, that is the dot product was 0, and the other condition is stupid, because that basically is saying that your matrix was already diagonalized. So why would you even do this anymore, right? So the second case, just ignore that, because if it's not 0 over here, then second case doesn't make any sense. So yeah, you can just forget about that, which means that you only care about the first case. So that is when sine beta plus cosine alpha equal to 0, and then with a bit of manipulation you can see that alpha and beta, they should have a difference of pi upon 2 modulo 2 pi, because there's like that should be there. So for example, if alpha is 0, your beta can be pi upon 2, negative pi upon 2, pi upon 2 plus 2 pi, pi upon 2 minus 2 pi, whatever, right? But the vectors should have an angle pi upon 2 between them, right? That's what I should have written, but whatever. This also works, right? So that basically guarantees that you can write our R and R inverses as rotation matrices, and of course inverses of each other. So what we can do is write R as c theta negative sine theta. Okay, I mean, just read the thing, I won't tell you the thing. And you will notice that this is not rotating by theta, so R is not rotating by theta but instead negative theta, which is weird. But yeah, I mean, I just how I want this to be, so I'll just write it by negative theta, right? I can do whatever I want. So that's how I'm defining R matrix, and then R inverse will just be this matrix, right? Okay, now we are getting to the main part, which is quadratic forms. So conic sections, they have quadratic forms at the very start. So basically, like any conic section, it will have a quadratic term, it will have some linear terms, and it will have some constant, right? So we are interested in the quadratic terms. So our quadratic term will be of the form ax square plus by square plus hxy, but then instead of writing this hxy and dealing with coefficients and all, I'll just be dealing with 2hxy. So yeah, just 2hxy. Now this thing can be written in this form: x times of ax plus hy and then y times of hx plus by, and that can be written as a dot product. So it's basically x comma y, this vector, dot with ax plus hy comma hx plus by, which can be written in this form. So basically you see that this is just a linear combination of x and y, this is a linear combination of x and y, so this complete vector is a linear combination of well, I should not say linear combination, it's just a linear transformation on x and y, right? So you can write it like that. Okay, so you have written q in this form. This can also be written in this form, which I don't like, but Wikipedia uses this for some reason. I really just like dot products instead of this, you know, this row vector, whatever this thing is. Why do they even use it? Anyway, once you have written in this form, you can start yeah, like dealing with this matrix. How can we simplify this, maybe give this some more intuition? Anyway, first thing first, notice that it's a symmetric matrix, which means that what we just learned can be applied over here. That this can be written as some rotational matrix times a diagonal matrix times another rotation matrix, which is the inverse of the first one. So yeah, basically it can be written like this thing. Yeah, so then q can be written as x vector dot rdr inverse of x vector, right? That's basically this times that, and x vector is of course this thing. So x comma y, x I hat plus y j, you know the deal. Yes, so you have written q like this. Now here's an important thing. Important thing is that rotating two vectors by the same angle, that does not change their dot product, right? I repeat, rotating two vectors by the same angle doesn't change the dot product. So look at this, you have two vectors, this blue vector times this purple-ish vector, and then you are rotating these two vectors by applying the R inverse matrix on both of them, and then you're taking a dot product. This dot product will be the same thing as this dot product, right? So q over here and q over here, they are the same thing. Yeah, and what that means is that you can actually use this thing, and then R inverse R is just, identity matrix. So this basically becomes what? R inverse x vector dotted with the diagonal matrix applied on R inverse x vector. Now let's call R inverse x vector as, I don't know, u vector, which can be written as u and v. And there you go, you can write q as u vector dot diagonal matrix applied on u vector. But now we know what the diagonal matrix actually is. It's just this thing, right? Lambda 1, lambda 2. So yeah, this basically becomes this thing. Lambda 1 u squared plus lambda 2 v squared. And also you might have noticed that you should actually have so this sine square alpha minus beta. What about this term? Shouldn't we think about that? Well, as alpha and beta have like pi upon 2 difference between them, plus 2 and pi, this thing just becomes 1. Sine square of alpha minus beta, yeah, it's gone, it's just 1 now. So really you can actually write our quadratic in this form, right? So our quadratic form can be written as lambda 1 u square plus lambda 2 v square, where uv are like u vector comma v vector is like the rotated x vector comma y vector, right? Rotated by the matrix R inverse. And now you will understand why I did R inverse as the matrix that rotates by angle theta. Okay, so that's good. Oh, and also remember what R actually was. It was just all the eigenvectors in order stacked up as column vectors, right? Of course reduced as well because we want them to be unit vectors, but whatever. Just remember that and you will be good to go. Okay, so let's start. So let's give you an example. First of all, consider this conic 11x squared plus 4xy plus 14y squared plus some linear stuff minus 1. Okay, we want to simplify this q thing, so you can write this as x vector dot, well, it's like 11, then you have 2 and 2, split that into half all the time, right? H and H, we saw that, and then you just have this thing 14 and then x vector applied on that thing. First of all, for diagonalizing this thing, you need to figure out the eigenvectors, for that the eigenvalues. So to the lambda minus thing, yeah, you know that, just or this thing minus lambda, yeah, you know the deal. It's just lambda squared minus 25 lambda plus I think 154, that's equal to 4. So lambda squared minus 25 lambda plus 150 is equal to 0, which means that lambda can be, well, okay, this can be written as like 15 times 10, so lambda is either 15 or it's 10, which means our diagonal matrix is, I mean, we already know that, it's just 15, 0, 0, 10. Now we need to figure out the eigenvectors first of all. So if lambda is 15, just, you know, subtract 15 from both sides, it will just be what? Negative 4, 2, 2, and that's going just negative 1, right? Okay. Right, so you want okay, this is probably just call this lambda 1, lambda 2, whatever. So sorry, v1 vector, okay, I should really just write everything down. Lambda 1 is equal to 15, lambda 2 equal to 10. We'll figure out what v1 vector and v2 vector are. So this matrix applied on v1 vector should be 0. So like think about a vector that has this property. You can write it like this thing actually, put that negative 2 up, okay, whatever, just an equation, right? So you can definitely take out constant, just 2, negative 1. So now, yeah, now, you know, just cut these things out because both are in fact the same thing. So think about a vector that is like basically perpendicular to this vector, right? Because it's just 2 comma negative 1, this vector dotted with v1 vector equal to 0. So 1 comma 2, right? This vector is perpendicular to this vector, I think. Yeah, sure. So what that means is, okay, first of all, we have to convert this to unit vector. So just divide by square root of 1 plus 4, 5. So this would be our v1 vector. So you got lambda 1 vector and, sorry, lambda 1. And our v1 vector is just, what was the thing once again? 1 comma 2 upon square root of 5. And what's our v2 vector going to be? I mean, we already know it's going to be perpendicular to this guy, just 2, negative 1 upon square root of 5, because this was the thing. But still, just to actually show you that it does work, put in lambda equal to 10 now. It just becomes 1, 2, 2, 4, and our v2 vector, that's equal to 0. So now you can see once again this is just 1 comma 2 but scaled up. So basically 1 comma 2 dotted with v2 vector should be 0. So of course v2 vector is just 2 comma negative 1 upon square root of 5, right? Unit vectors, oh, it should be vector over there. Okay, so now we know these things. Now we can construct our R. So R was just this thing, right? It was v1 vector, v2 vector as column vectors put out, right? So this will just be 1 upon square root of 5, and then you just put over there. So it's just v1 vector, just want 1, 2, and this would be just 2, negative 1. Okay, and R inverse would be what? It would be this thing, 1 upon square root of 5, and then yeah, just 1, 2, and 2, negative 1, I think. Wait, something's going wrong about this. I mean, these are not supposed to be symmetric. Wait, did I do this correctly or not? Just 2, negative 1, right? Or not? Maybe this was negative over there. Am I sure it's not supposed to be negative of this thing? I mean, it could be negative of that thing, right? It was like 1 comma negative 2. So why don't we like use negative 2 comma 1? I mean, yeah, that could be a problem actually. Oh, so I should have put another condition in my derivation that like okay the pi upon 2 stuff, right? These are still orthogonal and everything. It kind of does work out, except this is not what I wanted. So now it's not looking like a rotation matrix. But don't worry, because as I told you, our R is not supposed to be unique. So we can always change our R. We can modify such that it would work. So what we'll do is, instead of using this as a v2 vector, we'll just use this thing, negative 2 comma 1, right? Yeah, I mean that should be going good. Or I mean you could use 2 comma negative 1. There's no problem with that. But then wait, I think maybe I just messed up somewhere, or maybe like that. Okay, no need for that. So just use this thing. So this will become what? This will become 1 2, and then you just have negative 2 1. Now that looks more like a rotation matrix, isn't it? It does. So this inverse of the rotation matrix stuff. Remember, 1 upon square root of 5, that's a cosine value, and 2 upon square root of 5 is kind of a sine value. So then yeah, inverse of this thing is basically just change theta for negative theta, and basically just taking a transpose. So it's 1 2 and negative 2 1 over here. So that's R inverse. This thing is R. Awesome. So now that we have this thing, now that we have R and R inverse, so I mean we only need R inverse in the first place. Just set our thing u vector that's just equal to R inverse x vector, right? That's what we thought. And our R is in fact just this vector, right? Just go up. Yes, as you can see, it just the eigenvector is converted to, okay, put into this matrix and stuff. Yes. So you got this thing, u vector is just R1 R inverse x vector, which is 1 upon square root of 5 1 negative 2 2 1 times x comma y, right? So our u is just, well, x plus 2y upon square root of 5, and v is negative 2x plus y upon square root of 5, and our quadratic form will just become what? Well, what was our diagonal matrix? We got lambda 1 lambda 2 15 and 10, so this just becomes what? 15 u squared plus 10 v squared, right? Yeah, that's what this becomes. So instead of writing this, okay, this complete thing, we can just write 15 u squared plus 10 v squared. So our equation basically becomes 15 u squared plus 10 v squared. And now what about this thing? Okay, first of all, let me just clarify. I've just chose this into, it's like this is completely random. I didn't think about what this is. I just chose any any linear combination of our eigenvectors, and that's why it won't give us a nice thing. But anyway, what is this thing? 4x minus 2y. Well, look at our eigenvector, see if some linear combination of that works. If it doesn't work from the very start, then yeah, do the usual linear algebra thing, right? So a times of e1 vector plus b times of v2 vector equal to this thing or whatever. Do that thing, right? It shouldn't be that hard. Okay, actually not a times of, not the eigenvectors, we want the uv things, right? Yeah, so a times of u plus b times of v equal to this thing, and then figure out what a and b is. No big deal, it's doable now that we even know the inverse matrices and whatnot. Anyway, for this particular case, it's very easy to see what's going on. This is just negative 2 square root 5v, right? Yeah, just look at that. So this will just be negative 2 square root of 5v, and that's equal to 1 because minus 1 was there, so equal to 1. Yes. What does this become? Just 15u squared plus, so you know what, I should probably divide by 10. Yeah, I should divide by 10, I think, or maybe not, who knows. 15u squared plus, so I'll just take out that 10 for now, just 10 times of, okay, so let's do the by itself. Okay, fine. 10 v squared is there, and then now it's this thing. Interesting, isn't it? So that when you take that out, just that 10 is out now. It's just what is this now? 1 upon square root of 5v, right? So you just want 1 upon 2 square root of 5v. Oh, that's not there, not the v thing. Okay, this thing squared is equal to what? 1 plus 10 times, so 10 upon 4 times 5 or something, which would just be 20. So just 1 upon 2. So 1 plus 1 upon 2, right? Yeah, this is our conic, which now you can see just an ellipse. So it's 15u squared plus 10 times of, whatever this thing is, v minus 1 upon 2 sort of 5. I did it correctly, right? When I took that 10 out, it just, yeah, I mean, I definitely did that correctly. Right, I mean, like, what could go wrong? Yeah, so this is equal to 3 upon 2, divide by 3 upon 2 on both sides. Just come this. So like 2 upon 3 of this guy. Yeah, just have 5 on top, which is 10 basically over here. Divide by 3 upon 2, so it will become 20 upon 3. And now you can write it like this thing, upon 3 upon 20 upon 1 upon 10. So this is our conic, right? It's an ellipse with a squared is equal to 1 upon 10 and b squared equal to 3 upon 20, right? And centered around u equal to 0, v equal to 1 upon 2 sort of 3, which, I mean, you can just plug that into this thing and get the thing done, right? So yeah, I mean, u vector is just r inverse x vector. So basically x vector is equal to r times u vector. So r was what, by the way? R was this matrix 1 upon sort of 5, and then this stuff, just where did it go, 1 negative 2 2 1, okay, and this thing is applied on our u vector now, which is just 0, and then you have 1 upon 2 sort of 5, not, oh, that is actually square root of 3. No, it's square root of 5. Okay, that looks like 3, unfortunately. So just square root of 5 over there. Okay, cool. So what does this become? Just take that 1 upon 2 sort of 5 outside, just 1 upon 10 times, well, 1 2 negative 2 1, and that applied on 0 comma 1, right? Yeah, basically just negative 2 comma 1. So negative 2 comma 1 upon 10, that's the center of this thing. And also, I mean, just check this by itself, right? Let's check if that is in fact the center. I'm just gonna copy this, and to check that, what I'll do is just take some partial derivatives and see if that works out or not. So partial derivative of x should be 0 for our q, not just q, actually the complete c. So the condition for the center is basically like partial c upon partial x is equal to 0 and partial c upon partial y equal to 0, right? So for that, you just had 22x, that is just 4y, that is not there anymore, plus 4 equal to 0, and just have 4x plus 28y minus 2 equal to 0. And I just have to see whether or not these things work. Yeah, so let's put in the thing, right? So minus 2 is just minus 44 plus 4 upon 10, I guess, which is, yes, it is minus 4, and plus 4 equal to 0. So I mean, it already works from the first equation itself. What about this guy? Do I really have to show you? Maybe not. So minus 8 plus 28 is 20 upon 10 is just 2, 2 minus 2 is 0. So yeah, it does work. So predictions are correct, at least one of them is correct, and that, I guess, is satisfactory enough. So I have proved to you that this does work, and that it can actually be efficient. I mean, it's much more efficient than just random guessing, isn't it? Okay, so I'll just leave you here. Okay, so I'll see you guys in the next video.